We've already seen that gas and liquid molecules are in constant motion. And when the motion slows down, then we change phase. Now we're going to look at what happens when that liquid motion slows down and we start to freeze. So this is going to be energy added. And we defined this in a previous video as actually heat. So we have our gas, and the motion slows down when we get to a point. We called that the condensation point. Then condensation and evaporation occur at the same time in a dynamic equilibrium. So this is constantly changing, but it's at the same temperature. Then we have our liquid phase, and then that cools and the molecular motion slows down even further, and then we hit what's called the freezing point. So the freezing point is the point where liquids start to form crystalline or amorphous solids. Hit this freezing point, and although the molecular motion slows down when matter converts from a liquid to a solid, there is still going to be some molecular motion in a solid. The molecules or particles of a solid will either vibrate or shimmy in place. Now, a solid is characterized by having its particles be permanently bonded or fixed to its nearest neighbors. And a solid is much more dense than the gas phase. As the liquid particles start to fuse together, some of the fused particles will also start to melt. So what we have right here, this is freezing and melting. And these are opposites of one another. The heat of fusion is the energy required, so we're looking at H of fusion. Remember, HF is the heat of formation. We're looking at the heat of fusion. It's different. The heat of fusion is the energy required to melt 1 mole of a solid into its liquid. Now, it's also the heat involved in freezing 1 mole of a liquid into a solid. Once we hit this point, then we are at our solid. This is our solid region. This is our liquid and our gas. So when we go from a solid to a liquid, though, this is called the melting point, MP. The temperature of freezing and melting is static, and when we add or remove energy, that only causes the process to happen faster. It does not change the temperature. Freezing is an exothermic process, so we have exothermic when we're going this way on this graph. It's endothermic, so we're adding heat when we're moving to the right. So again, freezing is exothermic. It gives off energy in order to freeze. Melting is an endothermic process. It requires the absorption of energy in order to occur. So once a liquid freezes and it becomes a solid, that solid has a definite shape, a definite volume, and it's not easily compressed. A solid that has additional energy added will increase the molecular motion of the particles in the solid. Once the kinetic energy of the solid particles is equivalent to the melting point, again, here's our melting point right here when we're going from a solid to a liquid, then melting and freezing will occur simultaneously. So some of the particles will escape the solid phase and become a liquid. The heat of fusion is typically going to be much less than the heat of vaporization. We talked about the heat of vaporization in a previous video. It takes much less energy to melt a mole of ice. So the heat of fusion of water is 6.02, that's kilojoules per mole, than it does to boil 1 mole of water. To boil 1 mole of water, so the heat of vaporization is 40.7 kilojoules per mole. A solid can sometimes convert directly into a gas. So we can go from here to here, and that process is called sublimation. Some common solids that sublime, like solid carbon dioxide, dry ice, that sublimes. So does naphthalene. Naphthalene is in mothballs. Now, our water ice will also sublime, and you'll see this primarily in frozen food that's kept in a plastic bag. So the water sublimes out of the food, and then it's deposited on the inside of that plastic bag. And what happens is we notice that that food is then dried out. And that's what freezer burn is. Frost-free freezers also work on the sublimation process of water ice. There's air that blows over where the ice deposits and the ice sublimes. Now, when we form a solid from a gas, we call that deposition. And I mentioned that with the freezer burn example. When we form solids, we're either going to form what's called a crystalline or an amorphous solid. All of the images from here on out in this video were found in the Creative Commons OpenStax textbook. So here we have a crystalline solid. You see it's characterized by an ordered array of atoms or particles. And over here we have our amorphous solid. This will typically happen if the liquid freezes before the molecules can become arranged in an orderly fashion. There are also some liquids that simply are not going to form in orderly pattern. Now, an amorphous solid lacks internal structure because they're randomly arranged. Metals and ionic compounds will typically form crystalline structures. So this is where we're going to have our metals and our ionic compounds. Large molecules, so those are going to be harder to form an ordered pattern. So your larger molecules will form amorphous solids. And mixtures of molecules will form amorphous solids as well. Now, there are some substances that can form both, depending on what the conditions are when the solid is produced. But you're not going to be compounds are for my class. So let's talk more about our crystalline solids. For our crystalline solids, we can have ionic solids. Now, ionic solids are formed from ionic compounds. And this is an example of sodium. You can barely see that, at least I can barely see that on my screen. So if I have my, sodium, and here's chloride. Now remember, sodium is going to be larger than chlorine. We can do a little bit of final exam studying right now because they are in the same period, so they have the same principal energy levels available to them. The nucleus of sodium, it pulls on all of those electrons a little harder, makes it a little smaller. That's why sodium is denoted by the purple atoms here and chlorine by the green atoms that are slightly smaller. This is an example of a metallic solid. Now, a metallic solid is formed from metals, and metal atoms are held together in what are called metallic bonds. So metallic bonding is specific to metals that are bonding together. Now, all of these compounds will exhibit high thermal and electrical conductivity, and that's a typical property of metals that we gave earlier in the class. So the metallic compounds here, they're going to have metallic luster, and that shouldn't be a surprise. They will be malleable and high thermal conductivity. Now, the melting points of metals are varied. For example, mercury is a metal that is liquid at room temperature. Most of our alkali metals will melt below 200 degrees Celsius, and most of the transition metals melt above 1,000 degrees Celsius. These differences are related to the strength of the metallic bonds that hold the crystals together. The next type of solid is called a covalent network solid. Now these are going to be, solid. Now these are going to be comprised of covalently bonded compounds, and that's going to include the crystals of diamond, silicon dioxide, which is sand, or graphite even. Now are not only comprised of compounds that are covalently bonded, they are discretely covalently bonded to one another. So they're not just an intermolecular force holding it together, it's an actual covalent bond. Now, if we're going to study for the final exam very soon, it would be prudent to do a little bit of review. So what I want to point out specifically is looking at diamond and graphite. So notice on diamond how we have our carbon atom and it has 4 equivalent bonds to it. So it makes this tetrahedral shape. Now that tells me that it is sp3 hybridized. Over here on graphite, and I've drawn in a couple other, well, I didn't draw them very well, but I drew in a couple other hexagons here to try to show you this shape and see what is being bonded. So if I'm looking at this atom right here, which is difficult to see with this particular pen, and even if I color it white, then it sort of disappears. So this atom right here, then I'm looking at its 1, 2, 3 bonds. Now what this isn't showing me, however, and I can tell the way that these sheets are lined up, that this is a trigonal planar structure. What it's not showing me is that there is a double bond in there somewhere. So this is sp2 hybridized. And the difference in hybridization actually gives us very different properties for these allotropes of carbon. Now the next type of solid we're going to talk about is called the molecular solid. And it comes as no surprise that these are going to be comprised of molecules, covalently bonded molecules. But unlike the covalent network solid, the molecular solid is going to be held together with intermolecular forces. And so that's going to drive the properties of the molecular solid. Now something like solid elemental oxygen or fluorine, those would also be molecular solids. They are molecules after all. So here's an example. Here's iodine. And then here we have carbon dioxide. Now solid carbon dioxide is also known as dry ice. Now with the 4 different types of solids that we have looked at, we're going to look closer at the structure of metals. So we're looking at the metallic solids. Now we're only going to give this a quick gloss over. If you're really interested in this type of information, I strongly recommend that you look up a solid state chemistry course, especially the one offered by MIT as a free MOOC through edX. So here we have what is called the unit cell. And the unit cell is the simplest repeating unit in a solid. Now, a unit cell is going to have lattice points that lattice points are right here. They're the corners of my cube. And they're the locations of atoms or ions. Now, the entire structure will have this unit cell repeat many times in 3 dimensions. And the simplest is called the simple cubic structure. And that's what we have here, simple cubic structure, and that's abbreviated SCC. Now, the simple cubic unit cell, or the primitive cubic unit cell, you may see that in other books, has metal atoms arranged in one layer directly above or below and atoms in another layer. So you see they line up directly. These spheres are in contact with one another and they are not packed as closely as they could be. So they only take up about 50% of the cell itself, of the unit cell. And that's considered fairly inefficient. There's really only one metal that uses this structure, and that's polonium. And it crystallizes in the simple cubic structure. But that's the simplest of the cubes, so that's why we start here. Now you see there are 8 lattice points on the simple cubic cell, but it's not a whole atom at the lattice point. So if you can see from this 3D structure here, each lattice point, I'm going to circle that one. That's the one I want to look at. That lattice point is one atom, but that atom is shared equally amongst 8 cubes. So when we look at this unit cell, we actually look at it as if only 1/8 of the atom is inside of the unit cell. So we consider since it's 1/8 at each corner and there are 8 corners, we say there's 1 atom per unit cell. Now each one of these atoms, and here we're going to look at the big red one here, is touching 6 other atoms in the metal itself. So we say this has a coordination number of 6. Again, if you're moving on, if you're going to be taking a solid state chemistry course or something along the lines of material science, that's going to be an important concept for you. The next type of unit cell is called the body-centered cubic solid. So this one has an atom in the center of our cubic cell. And actually this particular image makes it difficult to pick out, but that red atom is actually in the middle. And we have our 8 atoms in the corners. So this time there's a layer of atoms in the center of each cube as well. So if we look at them top down, they're staggered. This is more efficient than the simple cell. So this is, again, the body-centered cubic, and we call this BCC for body-centered cubic. And this takes up about 68% of the entire cell. Now, any atom in this structure is going to touch 4 atoms in the layer above it and below it. So we say the coordination number of this is 8, but we say it has 2 atoms in the cell, and that's because we have 1 in the middle, and then we have 1/8 of an atom at each of 8 corners for a total of 2 atoms here. And there's going to be 1 atom total in here. Some metals that form the body-centered cubic solid include potassium, barium, chromium, molybdenum, tungsten, and iron. Then we have the face-centered cubic cell. Now the face-centered cubic cell, again, this image is a little bit odd. So the gray atoms are going to be in our corners. We still have 1/8 of an atom in each corner. Now we have 1/2 of an atom on each of our faces. Remember, a cube has 6 faces. So we have 1/2 of an atom on each face. We have 6 faces. So we have 3 atoms on our faces for a total of 4 atoms in this unit. This is the most efficient of the unit cells with atoms occupying 74% of the volume. This is called the cubic closest packing, or CCP arrangement. And here, let's see if I scroll down, we have some 3D representations. You can see the layers, and we have them kind of in a hexagonal pattern here to show how the atoms touch one another. Now, each one atom touches 12 other atoms, so the coordination number of a face-centered cubic structure is 12. Again, those coordination numbers will be important if you're moving on. In my class, I want you to be able to pick out which is which is going to be the simple cubic, body-centered cubic, or face-centered cubic, if given images sort of like that, but I hope to find better ones. And which solids would be formed from which compounds. If you have any questions, please reach out and let me know.